The average cost of dental work is about $5,350. A group thinks it's lower than that. A random sample of 29 people have an average cost of $5,225 with a standard deviation of 630. At alpha is equal to 0.025, can it be concluded that the mean is less than 5,350? These people have got to have the most crazy cavities on the planet, or they're going in for surgery or something, because that sounds outlandishly large. So let's go ahead and find this out. Now, just looking at the problem, look, we're only like, what is that, 350, 225? That's not that far off. So, this may be correct, just like looking at the numbers. Let's go ahead and see just if our intuition is going to check out with the math. So we need to figure out first what kind of test we're doing. So we're going to be doing a t-test. And the way you know that is that it says right here, with a standard deviation of 630, this standard deviation came from this sample of 29 people. It's a sample standard deviation. Because it's a sample standard deviation, we are going to be using a t-test. The other problem that we have here is that our sample is below 30. And different classrooms have different sizes for how big it kind of has to be. And it doesn't state that it's normally distributed. But because we're doing this in the section that we're teaching how to do this topic, we're going to go ahead and do a t-test. But just be aware that it really should say that the sample was normally, the distribution is normal. Because this is not enough people to by a lot of standards to do it. Some professors want 50, at least 50, others want 30. Just do whatever your professor says, but it really should say that as well. So let's go ahead and dive right into the hypotheses. So we're going to have two, right? We're going to have the null hypotheses, H0, and the alternative, H1, and we got to figure out which one's the claim. So H0 is the one that has the equals to. In this case, we're talking about an average. So it's the average is equal to, and then it says it's about $5,350. So the alternative is going to be the one we want to claim, and a group thinks that it is lower. So that means that they think that this claim at the mean is actually less than 5,350. So there we go. Now we want to see, can it be concluded that the mean is less than this? So this makes this the claim, H1, or the alternative. Some professors write HA. So this one is the claim. And from here, we can go ahead and do a couple of things. First, we could see that since it's a less than, that it's a one-tailed test. And we're specifically going to be shading on the less than side, so it's a left-tailed test. And knowing this, we can go ahead and pull some of the stats out of the problem. I like to have the numbers out of there. So first off, we could see our mean. I'm going to go ahead and write it again. We've got 5,350. That's the population mean. We're going to have a sample mean to go along with it. Our sample mean is 5,225. A sample mean's got to have a sample size. That's n. And we can see that's 29. And we're going to need a standard deviation. In this case, we are given a sample standard deviation, which gives us $630. And this is going to be our indication that we should use a t-test. And now what we're going to do is compute a test stat. Now we're going to do it two ways. We'll do it using the calculator, getting it just directly from the calculator. We'll also do it using the chart, because I know some professors require the use of the chart. So in either case, you should know the test stat formula. If you use the calculator, you don't need to know this technically, but it's good to know it. So we need to find our test stat. I'll do that in purple here, our test stat. And this is going to be computed from our samples and compared to our population in order to tell us, how close we were, if our samples supported what we're trying to claim here. So we're going to say, okay, well, the t, so our test stat is going to be x bar minus the mean over the standard deviation divided by the square root of n. Looks just like the z, except for we have an s instead of a sigma now. So X bar, let's plug all these numbers in. We got them all out. 5,225 minus 5,350. And look, just looking at this, we say, well, these are pretty close, but we have this whole bottom section here. 630, right? That's our standard deviation, divided by the square root of n, which is 29. And we can get this from the calculator now. So we're going to go ahead, pop this in here. We have 5,225 minus 5,350 over, we're going to go ahead, we're going to type another fraction, 630 over the square root, which is the second, and then the blue key here, 29. We do this, we get a test stat of negative 1.068. Now, this is our test stat. If we want to get this using the calculator, we just simply come over to stat. We go to tests, and there's a t-test, number 2. So we're going to choose that. We have statistics. These numbers here were computed from a group of data, so they're stats. So we're going to go ahead and choose that. And we've got our mean, 5,350. This is mu naught. Then we have X bar, that's 5,225. Our sample, standard deviation. So you see we have the S. It's a function of our data, X. And so we have that as 630. N is 29. So we're going to go ahead and put that in. And then here, so long as you write your mean on this side, you can just copy this symbol. So we have a less than sign. So we're going to choose less than, meaning to say that we think the mean is less than what we said our mu naught was, 5,350. We think it's less than, so we choose that one. And you can choose calculate or draw. Draw will make the graph for you, but the p-value is rounded a lot more. So we're going to go with calculate. So we can do the p-value method as well. You see we get a p-value here, very nice. So here we can see we get a t of negative 1.068. Check that out. I'm going to go ahead and steal the p-value right here too, because it's pretty convenient to have it right there. So we're going to have 0.147. We can get this from the chart as well. So from here, we have our test stat. We've seen the 2 ways of doing this. Let's go ahead and plot this sucker on a graph. So we're going to go ahead and put down plot. And it's a normal distribution. Well, it's not quite like a z distribution. It's a little different, but it looks similar enough that we just can sketch it the same way. In the middle, we're going to have 0, just like before. And we need to figure out our critical value. So we need that for our alpha. So we were told that our alpha, I should probably add it to our list here, is equal to 0.025. And so since it's a one-tailed test, this whole area is on the left side of the curve. So there's some area right here, and this is going to be where our critical value lives. Critical value, and this area is equal to 0.025 of the curve. Now we can get this from a inverse t using the distribution, right? Because it's related to a t distribution, or we can use the chart. We're going to do both ways. So first, let's do the calculator way. So it's a distribution, so we go to the distribution option. I see a lot of students get confused. I'm going to go to test and distribution. If you're doing stuff with test stuff, then you should go to a test menu. Like this is all test related, but this is a distribution and it's distribution related. So you should go to the distribution options. So we're going to do a second distribution, and we can see here, this is a t distribution because we're doing a t-test. So you need to go to the inverse t option, number 4. And in here, you can give it an area that's 0.025. The degrees of freedom we did not write down, but they're easy to figure out, right? It's just n minus 1. So in this case, n is 29, so our degrees of freedom is 28. And we're just going to hit paste. Hit enter. It's got to think for a second. And then we are given out the critical value. We are told that it's negative 2.048. Now, let's go ahead and check out what the chart has to say about this. So, and just to be clear, this 0.25, this is 0.025. This is an area. And so this area corresponds with the t-score of this. So if we go now to the chart, we could say, okay, well, let's take note that our degrees of freedom, let's add that to our list while we're here. That is equal to 28, right? N minus 1. So we're going to look up 28, and then we're also going to look up the 0.025 because we want 0.025 in one tail. So we're going to go to our t-table, and we can see here we are given some options here. We're told area in one tail or area in two tails. So in one tail, we've got 0.025, which we can see right here. And we're going to come down to a degree of freedom of 28. And let me zoom out a bit so I can see it on my screen. So this is the column we're interested in. And we want 28, which is this one. And we could see here that we get 0.048. And if we go back, we could see that that lines up perfectly to 0.048. Now this is negative, and we know it needs to be negative because look at this chart. There's no negative values anywhere on here because the chart is symmetric. So if you go around, if you want the positive side, you just take the positive of the number. If you want the negative, you just take the negative. So we're left-tailed, so we're going to take the negative. So that's how you would do it using the chart. Oh, while we're here, let me show you how to do the p-value as well. So this correlates to 0.025. Now let's say you wanted to find the p-value. Well, the p-value is the area covered by our test stat, right? So that's negative 1.068. So we're going to go to the t-table. We're going to look up negative 1.068 in the middle. And when we find it, we're going to go backwards and find the closest area that we can find. So we're going to look for 0.1068. So there is 0.1069. Wow, I found that pretty quick. Is there anything? 167. So it's going to be somewhere in this region. But the thing is, these are at different degrees of freedom, 17 and 18. We have to stay with our degrees of freedom. So our degrees of freedom was 28. So 1.0, and then we have 3. That's a lot. And then 8.5. So it appears that this is really the closest that we can get. Unfortunately, typically when you do a t-distribution, professors won't ask you this, but I've been in a few classes where I've helped tutor, and they do ask this. So I'm going to cover it. So for this, we just need to find the area that goes with it. So for this t-score, this is the closest one that we could get. Unfortunately, it's not super, super close, but it's close enough. If we come up and we look at the area in one tail, we can see that it's 0.15. And this is going to have quite a bit of rounding because we had to look it up like this and in a chart that didn't have them all. So if we have what do we have again? We have 0.15. If we come back here and look at our p-value, it rounds to 0.15. So not quite the most accurate, but that's how you would do it if you had to do it on a chart. You would have a p-value of 0.15. It's not as accurate, but that's how you would do it with the chart. So, okay, looking at all this, we can make a decision. We should plot our test stat, right? We have negative 1.068. That's somewhere over here, right? Because it's negative 2. So it's like right around here-ish. Negative 1.068. We'd say we are not in the shaded region, which is this area over here, right? And so we would say, therefore, we failed to reject or do not reject H naught. And so we do not reject H naught. This is the conclusion portion. And then we would say something about the claim. So if we don't reject H naught, so we're saying this appears that it could be correct because we landed in this white region. So then we say the claim, there is evidence to reject the claim. We can't say that the claim is outright wrong because maybe we just didn't get enough data, right? Only 29 people. So we would say, okay, well, we might have enough data. So there is evidence. We've produced evidence though, definitely, via our study. There is evidence to, or we would say it like this. This is the really nice way to say it. There is not sufficient So we're not even admitting that we're wrong here. We're saying we just don't, there's not sufficient evidence to support the claim. We wanted to support the claim, but we just didn't have enough. There was not sufficient evidence. In fact, we had evidence to say the other way, but we can't really say that, the claim was wrong. We just say that, we didn't have evidence to support it. And so we think that currently, we think that H0 has more merit than the claim does. And then you would say the claim that the average cost of dental work is lower than $5,350. You basically can just take this part here, that the mean is less than $5,350 for the cost of dental work, to tie it back to the problem. Now, if you're going to use the p-value method, we would compare p against alpha. And if p is greater than alpha, that means that the area shaded by p, which remember is the area according to our test stat, is greater than alpha. So we can see visually that's totally the case here. So you could also say p is greater than alpha, therefore all the same conclusion stuff. So this is a way you could sort of check your work as well. And that's how you do a question like this. So if you have any further questions about this question, feel free to let me know. Subscribe and hit that bell icon for future videos, and we'll catch you in the next problem.